Every autumn, a bird weighing less than a handful of coins launches itself into the dark and flies 2,000 miles, alone, at night, with no map. And it arrives at the same hedge it left the year before. For 60 years we couldn't explain how. The answer turned out to be stranger than anyone was willing to say out loud. Start with how little there is to work with. A European robin has a brain roughly the size of a pea. A first-year bird making its first migration has never seen the route before, and it doesn't learn it from the flock because robins migrate alone and at night. Whatever guides them isn't taught, it's built in, and for decades, nobody could find the organ responsible. The first hard evidence came in the 1960s from Wolfgang and Roswitha Wilczko. They placed migratory robins in enclosed cages with no view of the sky, no stars, no landmarks, nothing to navigate by. The birds still hopped persistently toward their migratory direction. Then the Wilczkos surrounded the cage with coils and rotated the magnetic field. The birds turned and lined up with the new field. Something inside the robin was reading Earth's magnetism directly. But the moment they looked closely at how it worked, it stopped behaving like a compass at all. A compass needle has a north end and a south end. Flip the field's polarity and the needle swings around. Do that to a robin, and it carries on as if nothing happened. What the bird responds to instead is the angle the field lines make with the ground. Tilt that inclination, and it reorients immediately. It isn't sensing which way is north, it's sensing which way the field is leaning. Then came the second oddity, and this one was the real clue. The compass only works in light. Under blue and green light, the birds orient normally. Take the light away, or shift it toward the red end of the spectrum, and the sense degrades or switches off entirely. That single fact rules out an enormous category of explanations. A piece of magnetic material in the body would work perfectly well in total darkness. It does not care what color the light is. But a chemical reaction driven by absorbed photons cares enormously. In 1978, a biophysicist named Klaus Schulten put forward an explanation that most biologists found difficult to take seriously. His proposal was that the bird's compass isn't magnetic in any ordinary sense. It's a chemical reaction whose outcome is steered by quantum mechanics, and the thing actually sensing Earth's field is a pair of electrons. The idea was, by the standards of the time, close to unpublishable. It sat on the margins of the field for the better part of 30 years. Here's the mechanism he described. When a photon strikes the right molecule, it knocks an electron from one part of the molecule to another. That leaves two unpaired electrons, one at each side, what chemists call a radical pair. Crucially, the spins of those two electrons remain quantum correlated. The pair oscillates between two configurations called singlet and triplet, and which configuration it occupies when the reaction finally completes decides which chemical product gets made. The rate of that oscillation is sensitive to the surrounding magnetic field. Change the field, change the ratio of products. That ratio is a signal, and a signal is something a nervous system can read. Which left one obvious question. If the compass is a light-triggered chemical reaction, what molecule is running it? The search converged on a family of light-sensitive proteins called cryptochromes, and in migratory birds, one version stands out, cryptochrome 4a. It sits in the retina, specifically in the outer segments of the double-cone photoreceptor cells, the part of the eye built to capture light, which carries a genuinely strange implication. The bird's compass isn't in its head in the way we'd assumed. It's in its eye. Earth's magnetic field may be something the robin in some sense sees. So researchers took the protein out of the bird entirely. They isolated cryptochrome 4a from European robins, purified it, and exposed it to magnetic fields on a laboratory bench, with no bird involved at all. The protein responded, its photochemistry shifted with the applied field. Then they ran the same test with cryptochrome 4 taken from chickens and pigeons, birds that don't undertake long migrations. Those versions responded far more weakly. The molecule most sensitive to magnetism belonged to the bird that most needs a compass. But the experiment that convinced the holdouts is the one worth understanding properly. Researchers exposed migratory birds to weak radio frequency fields, oscillating fields so faint they are millions of times weaker than a fridge magnet, nowhere near strong enough to physically move a magnetic particle. The birds lost their bearing completely, and the sensitivity is startlingly specific. Robins were disrupted at a frequency of about 1.3 megahertz in the local field, and that frequency shifted predictably when the background field strength was changed. That is not how a lump of magnetic material behaves. It is precisely how a pair of electron spins behaves. In this field, radio frequency disruption is treated as the diagnostic test, the result that separates a quantum mechanism from a classical one. It's worth pausing on why this is so hard to accept. Quantum coherence is notoriously fragile. In a physics laboratory, holding a delicate quantum state together means cooling equipment to a whisker above absolute zero, isolating it from vibration, and shielding it from stray fields, and even then it survives for a vanishingly short time. The robin appears to sustain something comparable in a warm, wet, chemically noisy eye, in a body that is actively flying. If that's what's happening, then our intuitions about where quantum effects can survive have been too conservative. Now the honest caveat, because the picture is not finished. The exact identity of the magnetically sensitive radicals inside a living, flying bird is still uncertain. Most of the direct chemistry has been done on purified protein, not inside the animal. A closely related protein, cryptochrome 4b, was investigated and then largely ruled out in 2025 because it doesn't bind the light-absorbing cofactor the mechanism requires. And recent work adds another condition. The protein appears to need to be held in an ordered arrangement against the cell membrane to function, meaning the geometry of how it's anchored matters as much as the chemistry it performs. This is an actively moving field, not a closed case. What makes this matter beyond ornithology is the precedent. If a robin can run a coherent quantum process at body temperature in the wet chaos of living tissue, then the boundary we drew between the quantum world and the biological one is in the wrong place. Researchers are now designing magnetic sensors modeled on the bird's chemistry rather than on our own hardware, because the bird's design tolerates conditions ours can't. Evolution appears to have arrived at a use for quantum mechanics several 100 million years before we worked out the equations. A pea-sized brain, a 2,000-mile journey, and a compass built out of electron spins in the back of an eye. The next time you see a small brown bird sitting on a fence in October, it's worth considering what might be going on behind its eyes. Does it change how you think about the line between physics and biology? Let me know in the comments. New discoveries unlock daily. Subscribe so you never miss one.